Okay, Namai, good afternoon. Today we are discussing the next remaining parts of the periodic properties, right? So last day we discussed one periodic property. What is that? First ionization energy, and then we did the what are the factors affecting periodic properties and like that. So I'll discuss those MCQs I gave as homework after the break and before finishing the class. Right. So today newly we will be discussing about three. I try to do all three. Let's see how it goes first. Right? Target is to cover ionized, electron gain energy, electronegativity, and radius. We'll start our discussion from radius, how the radius is changed. Right? So we can go to our tube. Periodic properties. Okay, online students, it's our tube. Yeah. Go to this fourth page. Okay, I'll tell you the what is this radius is. Simply, let's say atom is like a ball. Then the radius is simply the distance from the center to the edge of the ball. Okay, but atom is not a ball. That's a problem. Eh? Atom is like it was a ball at Dalton's time. Now, then after that, we had Planck pudding model. Still, it is look like a ball. So the same concept for radius. But then the planetary model came. There you had electrons moving in certain tracks. So then the radius will be the distance from nucleus to the last electron. Then there was Bohr model. Bohr model is slightly similar to this one, but in this one there was only one electron in one orbit. But here you have several electrons in one orbit. Okay, so again it will be the distance from the nucleus to the last electron. So up to Bohr model, it's really easy to define radius because we know definitely where the last electron will be. In O levels, you learn this that from many. But in A levels, the whole picture was changed. Remember, now what do we have? We have nothing. We have a probability cloud. Even in that probability cloud, we are not sure where this electron will be. What we have is only 99% probability. There's a chance that our electron may not be there also. Okay? So now things are getting a little bit difficult. According to A levels atomic model, let's say hydrogen is having electronic configuration is 1s1. Okay, so that electron can be basically anywhere in this case. Outside the also. That's simply what it is. Did you learn about this from somewhere? Okay, now we are believing atom is something like this. Earlier, you thought that hydrogen electron is moving in the Bohr model energy level. Now there are no energy levels. Now there are probability clouds. These are the possible places for that electron. It can be one place. We don't know which one. We can't be sure. Maybe this. Or it may be this. Or it may be yours. Who knows? And now defining radius is really difficult. Isn't it? There's no certain distance. If the electron was here, then that's the radius. If the electron was here, then this will be the radius. If the electron is outside, this will be the radius. So now we face a big problem. Now, what is the solution for this? The solution. We wait until atom now electrons are really free now, can be any location. We wait until it is limited to a certain location. We wait until it is limited to a certain location. Like when it is making a bond. Okay. When it is making a bond. So after making bonds, electrons can't go here and there. They will be limited to a certain location. Our next lesson is bonding. In that lesson, we will discuss this. Right? Now, take for example hydrogen molecule H2. How did you draw hydrogen with no levels? H2 molecule. Emily, the way you drew. So in A levels also we are drawing it in the similar way because hydrogen is having spherical s orbitals. Similar way, right? And now these are the nuclei, and now the electrons are limited to this location. So it can't go here and there. If they went here and there, then the bond will be broken. There will be no H2. If H2 is there, then electrons must be, can't say must be, again, probably will be here. Okay. So then what we do is now, we get the distance between the nuclei. Let's say it is D, and to get the radius, what we do is we divide that one by 2. So we define it as the radius. But again, small problem is, if you divide it by half, you will see it is less than the actual radius. A small part is missing. Okay, so that means we can't get a perfect answer. But this answer is better than having nothing. And so this is called covalent radius because this was a covalent bond. Depending on now, all atoms are not making covalent bonds, then there are hundreds of atoms. Out of that, 92 are naturally existing, 90 to 95. So most of the elements are metals. Sometimes metals are not making covalent bonds. So then we can't achieve this state for everyone. So depending on the bond they make, we define radius. Like this one is covalent radius. Then there is a thing called, I'll explain everything. Okay? And there's a thing called van der Waals radius. Depending on the bonding, we identify van der Waals radius. And there is one called metallic radius. So for metals, we define metallic radius. For covalent bond forming molecules, atoms, elements, we define covalent radius. Like the helium, neon, argon, remember. Those are noble gases, they don't make any bond. For them, we have van der Waals radius. Like that. Have you heard this van der Waals word before? No. Have that. Because there are somewhere. Biology. Hello, guys. Not in all levels. All levels you had hydrogen bonding. Hydrogen bonding word was there in all levels. Don't worry, we're going to discuss anyway. Right, so my point is, you understand. Now, according to A-level atomic model, we can't be sure where this electron is. So to define the radius, we have to wait until it makes a bond or something. Right? So when you make a covalent bond, simply we get the internuclear distance and we get the word internuclear distance. The distance between nuclei. We get the internuclear distance and divide by 2. Then we get the covalent radius. And for those who don't make any bond, there's another method to do that. Like that. We have wait until it makes some sort of attraction to measure the distance between two nuclei and divide it by 2. Okay, it's true that atom has no boundary. Now, when I was teaching last week, one student asked this question. Some of the class he asked how if the quantum atomic model is true, electron can be in multiple locations. Then. So how do we measure the radius? It's a good question. So we can't measure the radius exactly. We measure it something like this, some way like this. Okay, Laman. So now you got the idea about the lesson. Now shall we go to the page number 4? Yeah, one online student is asking whether we can get ionic bonding for this thing. I'll explain. We can't take ionic bond. I'll explain. Okay. Right. We'll go slowly through this page. We'll understand it perfectly. According to the quantum atomic model, atoms do not have sharply defined boundaries. Can understand? Okay, you can explain further. Okay, so underline have no sharply defined boundaries and right. Electrons are existing in a probability cloud. Electrons are existing in probability clouds, not in certain tracks. Electrons are existing in probability clouds, not in certain tracks. Not in certain tracks. Not in certain tracks. Not in certain tracks. Probability clouds, not in certain tracks. We can define atomic size in several ways based on the distance between atoms in various situations. Underline various situations and say when it makes bonds. Underline various situations and say when it makes bonds. When it makes bonds. Now in science, what do we do, Lama? We see a problem and we try to solve that. It's our main purpose. Okay? Everything is like that. So our problem is now finding the radius. A huge problem. Now I'm going to solve that one in a way that everybody can understand and it will be fair way also. Now we are defining covalent radius first. Read the definition. A chemical bond is the attractive interaction. Pay attention to the words. So if you understand, if you don't understand any word, ask. Okay? Then you will get the meaning. Right? A chemical bond. Chemical bond. Is the attractive interaction between any two adjacent atoms in a molecule. So for example, if it is H2, hydrogen atoms are the adjacent ones and those are attracted. So it's the attractive interaction. Can understand. So that's the one we represented later in all levels later by a dash. Chemical bond is represented by a dash. And this is representing the electrons that the two electrons that are overlapped, dot and cross diagonal. Those are there in the next unit. Unit 2 bonding, we'll discuss them. But here they are simply telling this is a chemical bond. Can understand? And the two bonded atoms are closer together, then they would be in non-bonding collision. Non-bonding collision means without bonding. After bonding, they get overlapped. That's why they are kind of closer. Yeah. The bonding atomic radius for any atom in a molecule is equal to the half of the bond distance. Okay. The distance between the two bonded atoms. Half of the bond distance. The bonding atomic radius, also known as the covalent radius, is smaller than the non-bonding atomic radius. I'll explain now what is non-bonding atomic radius. But before that, shall we highlight the definition? The bonding atomic radius for any atom in a molecule is equal to the half of the bond distance. Half of the bond distance. Bonding atomic radius for any atom in a molecule is equal to the half of the bond distance. Okay, now let's pay our attention to the diagram we have. That will explain everything nice. And it is a molecule. It shows you two I2 molecules. Can you see? Two I2 molecules. Right? The one that are overlapped slightly is one molecule. And there's another one. Like So can you see when they are overlapping, you have the covalent distance. What is the covalent distance? 266 picometers. PM is picometers. You know, it's a very small length. 10 to the power minus 12 meters. Okay? It's a very small. And covalent radius is exactly half of that. And what is this van der Waals distance? Van der Waals distance is there is no bond between them, but those are attracted to each other. I'll explain how it is happening. And anyway, it is measuring the distance between adjacent nuclei. Can you see can you see the nuclei they have considered for van der Waals distance? Those nuclei belong to two different molecules. Okay? Adjacent molecules. And then you get the distance between them, and then you divide it by 2, you get the van der Waals radius. As we expected, van der Waals radius is significantly higher than covalent radius because there's no overlapping. Understood? There's no overlapping, simply we can say. So near covalent radius, say smaller because there is no overlap. Smaller because there is no overlap. So because there is an overlap. Don't say no. There is an overlap. Covalent radius is smaller because there is an overlap. Van der Waals radius you can say larger because there is no overlap. Okay, no overlapping thing you have to add to van der. I'll tell again. For covalent you have to say smaller because there is an overlap. For van der Waals you have to say larger because there is no overlap. There is no overlap. So I'll explain this van der Waals interaction real quickly. Van der Waals interaction real quickly. In our bonding unit 2, we discuss all possible chemical bondings that can occur between elements. Now, here's the thing. In chemistry, we learn first about atom because that's the fundamental part. We need to understand atom in order to understand what is happening with atoms, molecules, those things. To understand them, we need to first understand atom. That's what we are doing. Now we are checking the atomic radius. Something we need. And after knowing that those areas, we are discussing in the second unit about the bonds, the various bonds they can make. So we divide that bonding unit into two main areas, just like we did for atomic structure unit. Atomic structure unit also we divided atomic models and periodic properties. Like that, this is also divided into two about primary interactions and secondary interactions. So these are called bonds also. Bond. So the word bond is carrying some heavy meaning. Bond is something kind of strong. For these we don't call bonds. These are called attractions. Attraction. It's kind of, it implies it's not that strong as a bond. Then primary interactions, there are three types. In all levels, you will learn two. And remember, covalent, ionic are the two you learn in all levels. In what is happening in the covalent bonding? Sharing of electrons. Now we don't say sharing. We say overlapping of atomic orbitals. Same thing, sharing of electrons. The technical word is overlapping of atomic orbitals because now we have different shapes of orbitals. They can overlap in this way, or they can overlap in that way. Everything will be discussed later on. Anyway, they get overlap. Overlap means a bond, a strong bond, covalent bond. Understood? Overlapping of atomic or the proper definition. Atomic or hybrid orbitals. Now you learn about atomic orbitals only. Later you will learn what are these hybrid orbits. I'm going to discuss too. Anyway, it's of course an overlap. So this is the one that guide us to covalent radius. Okay, you get the half of their distance. Then what do? You get the half of this distance and divide it. You get this distance and divide by 2. Okay, then it will give you the covalent radius of this point. Get the idea? Now earlier in O levels you draw everything as circles. Now we can't do that. There's no such circle. Correct? Then in ionic radius, what is ionic bonding? What is happening? Exchange of electrons. Okay, still we kind of treat it like exchange of electrons. Example, sodium plus and Cl minus. Okay. Anyway, this is not relevant for our today's radius topic. So we'll put a bracket. No point of discussing about it. There is a third type of bonding, a primary bonding, a good bonding. That is named as metallic bond. Metallic bond. So I'll explain a little bit about metallic bonding. You know metals, sodium, and then metals like iron. Two different, no? Two different elements, two different metals. But any metal share certain characteristics that are not having in other covalent compounds or ionic compounds. What are they? You can hammer them into sheets. You can draw them into wires. Metals are having this nice luster, and they are good thermal conductors. They have a set of different properties. But those properties can't be explained by covalent and ionic bonding. For example, electrical conductivity. Okay, to conduct electrons, there must be electrons. To conduct electricity, there must be electrons. But the electrons, if you are having covalent bonding, electrons are now trapped here. They can't go here and okay, so that means they can't conduct electricity. In an ionic bonding also, that electron is permanently gone to C and orbit. Then again, it can't also conduct electricity. So electrical conductance is not explained by these models. Models. So to explain electrical conductance and other properties of metals, we have a different model. That model was not needed in all its form, but now we need. Okay, so we say something like this. We say, if it is sodium, sodium is having 1s2, 2s2, 2p6, 3s1 electronic configuration. Those who don't know this one, it is same as 281. Right? And this one is loosely bounded. So we say if you are having set of sodium atoms, they all releases their single electron and they make a pole of electrons. Pole of what? Pole of electrons. If you are having more electrons like that, let's say aluminum, iron, they are having more electrons. Those electrons are gone as free electrons and make a bigger pole. Like you take iron, for example, you take the same volume, V volume, and it is easy to compare. Iron atom is very small, and it is having large number of free electrons. That means last energy level electrons are given to this pole of electrons. Right? And now electrons are negatively charged. Nucleus or the atom, positive nucleus of the nucleus, positive ion of the metal ion is positive, and they will have these attractions. We represent these attractions by these small broken lines. You can understand. Here you have fewer number, but here you will have larger number. Isn't it? I mean, I will mark them every number of attractions. Okay. So then this model can explain everything. Why they are electrical conductors, Because these are free electrons. Free electrons. That means those electrons are not attracted to one metal ion. They are attracted to mutually for all metal ions. Then if you push these electrons by giving a voltage, these electrons can slowly move towards other side. Because when you are pushing, electrons are also newly coming, and electrons are not. So it can conduct, let's see. Right? And those are not the rigid doors. You can break, you can't break them. And what you can do, you can have them into sheets, drawn into wires. Why? Because it is flexible. And they maintain the strength also. Okay? This is the model case. And then what's the other thing? Yeah, those are the things that basically metals are having. So basically any property can be explained. And you can explain why sodium can cut with a knife. The knife is iron. The iron is harder than sodium. You can explain that also. More metallic bonds. Lesser metallic bonds like that. Sodium is a soft metal. So you will learn about them in proper notes and more explanations. But I'm just roughly telling you today only because it's needed for today's discussion. So anyway, this is the form we can find for the most of the periodic table elements. Because most of the elements are in our periodic table are metals. And this is the best attraction we can find for them. That's why we are getting the internuclear distance here. D metal. You get the distance between two metal ions. Because they are regularly arranged, you can see they are nicely arranged. So you get the distance between them. And it will give us the metallic radius. If you divide this one by 2, you divide this one by 2, you get the metallic radius. Now understand. Covalent radius is the half of this. Metallic radius is the metallic bond, half of the internuclear distance. And there's one more. What is that? Van der Waals. So let me explain Van der Waals. Van der Waals. In secondary interactions, there are 6 secondary interactions. Don't forget. Easy, I say the one type of secondary interactions are there. IMAs. IMAs can intermolecular interactions. You have molecules. The molecule is one type of building block we have. Intermolecular attraction. So intermolecular attractions. Intermolecular attractions. Attractions. So there are various types of intermolecular attraction. Those are not that critical. You can easily remember them. So, but my point is, Ramai, molecules are attracted to one another. Now, inside this, they have a covalent bond. Inside this, they have a covalent bond. It's like the I2 example. And these two molecules are attracted from this end to this end. Okay, so how it is happening is not important for you right now. Just believe there's an attraction. Is how it is happening. We are explaining in the second unit. Just wait one more month, 1 to maybe 2 months. And there is a plus minus attraction happening. And now the nucleus, now the attracted molecules are these things. Now, if you get the distance between these two nuclei, that is the Van der Waals distance. And these attractions are called Van der Waals attractions. Van der Waals attractions. Those are not, you don't call Van der Waals bonds. Bond is some heavy word. We say Van der Waals attraction. We call, when you, now let's say, when you heat this one, the bond that is going to first break is this, the weakest one. When you heat it further and further, then only covalent bonds are broken. It's very difficult to break. That is very much. For example, if I give you some values, if you assume this has 200, this will be like maximum 20, 10 folds larger. At least 10 folds larger. Now understood the 3 distances. They are scattered in the lesson. The lesson will come, we are expanding and teaching. In the second lesson, you have a nice flow chart at the first page. Everything will be included, all the topics and everything like this. There are more to add here, okay? And so this is the summary that we need for today's discussion. Now shall we go through that bonding and unbonding, that part? You can understand. Now we don't call this as a bond. This is not a non-bonding. This is not a bonding. It is an attraction. So that's why this is called non-bonding atomic radius. Okay. Now look at that van der Waals radius term. The van der Waals radius or non-bonding atomic radius, underline both. Highlight non-bonding atomic radius is better. They can start MCQs by their name. They can tell this is the non-bonding atomic radius of this and then compare and ask questions. So non-bonding atomic radius refers to 1/2 of the distance between two equivalent non-bonded atoms in their most stable arrangement. Highlight that. That is the definition. Now in that above diagram, everything is represented, right? Bonding and non-bonding atomic radius. So what is important for MCQs is the definition. No need to write them. Either they are not going to ask anything to write. You have to remember them by words and all to identify this the proper definition. And then again, you need to remember van der Waals radius is always larger than covalent radius. Okay. And then the final one, metallic radius. Now you know about metallic bond. Metal atoms in a metallic structure are bonded to each other by metallic bonds. Half of the bond distance between nuclei of two adjacent metal atoms in a metallic structure is called metallic radius. Okay. Those are the metallic radius. So we can't say their length is higher or lower. Now here's no overlapping. But we can't say it is larger than covalent radius. But why? Because here they are making a cation. When cations are formed, positive ions are formed, they remove electrons. As the electrons are removed, they become smaller. Who knows it is smaller than the covalent bond? So we can't compare metallic radius actually with others. Okay, what we can do is compare covalent and van der Waals radius. Understood? So what's the summary of this discussion? Summary is this. It says electron location is uncertain. We can't say where the last electron is. Can't be sure where it is. Okay. So what we do is we have the possible locations, and it is not enough to get a proper radius. So we wait until it makes an attraction. Okay. So there are 3 possible attractions we get to find the radius. Covalent attraction, we say it is covalent bond. And metallic attraction, we call it as a metallic bond because it is strong. And then for some cases, they are nothing like helium neon wagi. We get this van der Waals attraction. Okay. So in each case, what we do, we get the adjacent, the distance between adjacent nuclei. Okay, and then we divide that one by 2. Then we get the radius. Okay. For I2-like molecules, we can get van der Waals radius and covalent radius both. Okay, let's say helium. Helium is not making any bonds with another helium atom. It will just make this attraction only. Helium will be like this. Attracted by van der Waals attraction. So then for helium, you have a van der Waals radius only. Like that. And sodium is a metal. So you have metallic radius. Sodium can make Na2 molecule also. It's a special condition. At a certain high temperature, it can make a molecule like H2. Then it is having a covalent molecule, covalent radius, van der Waals radius, and metallic radius, everything. For some elements, there are all three. But elements like sodium. For some, only one. Understand? So we are using kind of when we are having several things, we get the average. If you have only one, now let's say hydrogen, helium. In this case, we do a small error correction. You're not supposed to learn that part, but we adjust the radius mathematically. There are ways to do that. Then you get a proper radius without any errors. Now you understand this is higher than the actual radius. But when they make tables and period table graphs, if when they are including radius for helium, that is the corrected radius. And that's the proper radius by mathematically, and other ways you can correct that mistake. Correct the now we have overestimated the radius. You can correct that finally. There are methods to do. But first, at the first place, we need to get some value. We are learning that part on how to get the value, not the error correction. Understood me? Okay. So then, so metallic radius. Now, that's the summary, okay? Again, if you put it in 3 sentences, we can't measure the actual distance of, we can measure the actual radius because now the elements are, atoms, electrons are uncertain. Therefore, we wait until it makes a bond. We take 3 bonded situations, get the distance between adjacent nuclei, divide by 2. Okay. Covalent, van der Waals, metal. Bonding atomic radius is covalent. Non-bonding atomic radius is van der Waals. Okay. That's something. Now let's go to the atomic period trends in atomic radius. Okay. Now why we had to go through that earlier half an hour discussion? Because when we discuss radius, is this picometers, that picometers, you might wonder how the radius is measured. Now you know how it is measured. Okay. So then the main MCQs and questions asking on this lesson will be based on based on the things now we are going to discuss. Okay, because we need to explain why sodium radius is larger than magnesium. Right? Why sodium radius is larger than lithium. Downward the group radius increases, across the period it decreases. We need to explain why it is happening and we need to compare them. Remember last week ionization, we did there were questions. They were asking the correct order. And those are the main questions that can come. But remember that radio explanation will be important something for some questions. Can't be sure. But now we are the part we're going to discuss now definitely will be there in your paper. Okay. Now, tell you about that. Atomic sizes. The atomic sizes within a periodic table shows 2 interesting trends. We'll see whether it is interesting or not. What is the first one? Within each group, what is happening? The atomic radius tend to increase from top to bottom. Atomic radius tend to increase from top to bottom. Okay, atomic radius tends to increase from top to bottom. This trend results primarily from the increase in the principal quantum number of the outer electrons. This trend results primarily from the increasing in the principal quantum number n of the outer electrons. Okay, so we will highlight first increase from top to bottom, that part. And what is the reason for that? Increase in the principal quantum number. If they ask for a reason, that is what you need to give. Increase of principal quantum number. As we go down a column, the outer electrons have a greater probability of being further away from the nucleus, forcing atomic radius to increase. So they explains now why downward the group radius increases. Can understand? Is it convincing for you? Number of energy levels, okay? Then boys, what do you think? Number of energy levels, can understand it. Okay, now go to the next part. Within each period, atomic radius generally tend to decrease. Highlight that. Generally tends to decrease from left to right. Okay, look at how we explain that one. The major factor influencing this is the increase in the effective nuclear charge across the period. Increasing effective nuclear charge steadily draws the valence electrons closer to the nucleus, causing atomic radius to decrease. So highlight, underline, or highlight that part. Okay. Last part. The increasing effective nuclear charge steadily, that last sentence, is the one you need to remember. Effective nuclear charge. Effective nuclear charge. Okay. So now how do we explain that one? Radius downward the group radius variation is explained by number of shells. Remember that word, number of shells. Across the period, variation is explained by ZEFF. Shall we write that short version also? New effective nuclear charge is termed as ZDF. ZDF.
We use calculations.
Huh?
We use radius to explain nuclear. Sorry.
Now, ZDF explain කරන්න radius ගන්න. We use radius to explain FEF, attraction force. Okay. That's why I skipped it. And someone can say, it's a good point. Someone can argue me, attraction increases, that's why size decreases, no? See, nuclear attraction increases, that's why size decreases. But we can't tell it because inside attraction we have radius. You remember last week formula? Go to the page number 2 and see that. Page number 2, go to that one and see. In page number 2, you have those formulae. You might have the completed notebook theory. ZDFF is affected by Z and sigma. Z is nuclear attraction, sigma is shielding. There's no radius. But FEFF, that's the most suitable way. But FEFF, that one we can't use. Why? Because FEFF is affected by radius. To explain radius, we can't use radius. Simple. That's why we have to use FEF, ZDFF only. Otherwise, FEFF is the best way, but we can't go there. Inside that, we have radius. Clear? That's why I asked you to memorize what to write. When you are explaining radius, if you write fraction increases, that's why radius decreases, that is not that good. It's correct, but not properly organized. The best way is telling about is ZDF. Okay, because when you want across the period, ZDFF steadily increases, gradually increases. You can say with that, since the nuclear charge is increases, electrons are more drawn towards the nucleus. But it is attraction. But we can't use that word. Don't use attraction word. Now, understood that? Okay, now you know what to write in a short structured essay question. If they ask you to explain downward the group variation, you can write that highlighted sentence. If you are asked to write across the period variation, you can write the last sentence. Effective nuclear charge steadily draws the valence electrons closer to the nucleus. Okay, so our neighbor might not know about the effective nuclear charge and others. But anyway, you understand what is happening to the radius. There's a proper way of writing the explanation. For that way, we need some proper words. Traction, shielding effect, like that. Some heavy words were there. We discussed that last week. So you can go through that recording and finish it properly. Right? So now just try to understand the crude meaning. Okay, radius increases or decreases. Okay, that is why. Yeah, like that. Just try to think roughly. That is enough. See whether we can do the questions in that way. We can test. There are questions. Now, shall we all go to the page number 5? There you have a table which I got from your resource book. That gives you the values of the radius. First of all, no need to memorize any value. Right? But look at their shapes, sizes. Right? Across the period, it decreases. True. Downward the group, it always increases. Downward the group, it always increases. Later, we will come back to this table. Now, go to the next part. Oh, no. Before there's any previous thing, before going that, I need to show you some pattern. So that is a nice pattern we can remember. Take lithium, beryllium, sodium, magnesium, the 4 squares adjacent to each other. Lithium, beryllium, sodium, magnesium. Can you check those 4 squares? Lithium, beryllium, sodium, magnesium. Check their values. Beryllium is the shortest one. Then lithium, then magnesium, then sodium. So now tell me, lithium and sodium or beryllium and magnesium, you can easily compare. What if they ask you to compare lithium and magnesium? Which one will be higher? Magnesium, you need to give a reason for it. Because magnesium is in to the right of the group. When you go towards right side, radius decreases. Okay? So you need to give an explanation. Most of the time, almost, most of the time, downward the group variation, downward the group is reason is there now increasing number of energy levels. That effect is more powerful than ZDF most of the time. Understood? That's why when ZDF increases, the size decreasing. That's why magnesium size is smaller than sodium. Right? But when you compare magnesium and lithium, magnesium is having a higher radius, not because of ZDF, because of the energy level effect, shell effect. Understood? So you can put a star by the side and say, I'll give you a statement to it. Put a star and write. Put a star and write. Radius of magnesium is larger than radius of lithium. Most of the time. Increasing shells or energy levels. Energy levels effect is more powerful than is more powerful than ZDF effect. Because effect ZDF is trying to decrease the radius. Right? Now this one is having magnesium is having a higher ZDF. But still radius is large. That's the reason. Now if you carefully look that part again, we can establish a simple rule. Right? Those are tricks for your MCQs. If you get 4 elements that are adjacent to each other, like that. Let's square. Let's take lithium, beryllium, sodium, and magnesium. You don't need the values now. You can simply say they are changing in this order. Can you see that one? Like this, can you see? In this order. Because look like a Z, letter Z, but when it is set in front of a mirror, okay? It is a mirrored Z. Normally you write Z in this way, you put it in front of a mirror, it look like this thing. So this is a mirrored Z. So atomic radius is changing according to a mirrored Z. Now go to that about table. Now the thing is this now. When they ask questions in A-level exam, you can see for yourself today. They are mainly asking the downward group proper period questions are easy. Then they will normally join this theory also. They will try to make you confused by giving lithium and magnesium together. You need to think how is it lithium or is it like that? I think in that thinking, this rule is very useful. But this rule is not applicable for all the places. There are a few places you can check from your graph and find out what are the places this rule is not applicable. What are the 4 boxes? Go through 4 boxes, 4 by 4. You can do it as a small activity now and find out which one is not applicable. To which set of 4 squares this method is not applicable. Now, shall we go together now? You have to omit hydrogen and helium. Then, and start from lithium, sodium, magnesium, beryllium. That is square is okay. And then go to the beryllium, boron, magnesium, aluminium. That is also okay. Beryllium, boron, magnesium, aluminium. And then boron, carbon, aluminium, silicon. That also. Carbon, nitrogen, silicon, phosphorus. That also. Nitrogen, oxygen, phosphorus, sulfur. Okay. Oxygen, fluorine, sulfur, chlorine. Okay. Fluorine, neon, fluorine, argon. That is also okay. That means first 2 periods, the first 3 periods, second period and third period, there's no problem. And the most they are asking that. Right? Then is the 4th period. Sodium, magnesium, potassium, calcium. Sodium, magnesium, potassium, calcium. So calcium is larger than sodium. So okay, fine. Then go to the magnesium, aluminium, calcium, and gallium. And gallium is smaller than magnesium. There are places you can't apply. But don't worry, they will never ask that. Without the values even, we can't predict it. Okay? So they will ask some place where you can predict with that Z. Okay. And then look at the next one, aluminium, silicon, gallium, germanium. That also not applicable. Phosphorus, sulfur, arsenic, selenium. That is applicable. Okay. Then sulfur, chlorine, selenium, bromine. That is okay. Chlorine, argon, bromine, krypton. That is also okay. So now you found 2 places where this is not applicable. Okay. So shall we put commas and write where this is not applicable? So no need to worry about this much about the metallic bonding and others. I saw one lecturer is asking to explain metallic bonding again. So don't worry. There's a separate whole day for that one. I can explain it to you multiple times. Don't worry about that one today because trying to understand that kind of a topic today is kind of useless. Just I told you this anyway because there is something called metallic bonding. So understanding roughly is enough. Okay, so just try to understand today why metals are conducting electricity. That is enough for me. Honestly, that is enough for me. But earlier you didn't know that why metals are metals are conducting easily, but when they ask why, there's no reason. There's no scientific reason. Okay? But now you know why. Because their structure is made of free electrons. All metals in their last energy level, those electrons existing in the last energy level, they release those electrons and they make an electron pool. So because of that, pool is kind of free to move around. While it is attracted to metal cations, they are free to move around. So then those electrons can conduct electricity. Understanding that is it. And the distance between the two nuclei is the one we measure. That's the one part we need for today. Understanding that part is enough for me. Right. Now, where these are not applicable of those four things, magnesium, aluminium, calcium and gallium. Okay? Calcium and gallium. This is not applicable. Then you found aluminium silicon. Then the other one gallium and germanium. Germanium, this is not applicable. Then others are okay. So in first four periods, that's the only place, those two are the only places that we can't apply this. Now let's expand our discussion to fifth period also. Now check potassium, calcium. Now check with me. Potassium, calcium, rubidium, strontium. Again it fails. And so they will not ask about that from the exam. Potassium, calcium, rubidium, and strontium. It fails. Then calcium, gallium, strontium, and indium again fails. Calcium, gallium, the other one, strontium and indium. And then gallium, germanium, indium, and tin. Those are equal, same. Then arsenic, sorry, germanium, arsenic, tin and antimony, Sb. That is okay, ne? That is okay. Then arsenic, selenium, antimony, and terolium. That's also okay. Others are okay. Check. Yeah. Ne? So that was there. But the one I didn't write 140, 140. Gallium, germanium, then indium and tin. Equal එකක් ගන්න ඇති. මේව අහන්නේ නැහැ. But I'm sure. These are not following the mirror set, so will not be asked in the exam. That's a point. Otherwise, you will memorize them. Yeah, need change this. Should study it. No, don't study. They will never ask. Okay, but I remember this only. Again, when I'm making papers to you, I'm making the questions. If I accidentally put this one, then technically it is wrong. So I remember this one as a teacher, not to include questions from this. Because I can't apply it to this. That's it. Okay, for you, it's not me. Right, so then if you go further, you will see that variation is continuing. Then the last one, rubidium, strontium, cesium, barium, again, it doesn't follow. So that means in S block, only the first few rows are okay. Then after that, it is breaking the rule. Right? Okay, so shall we write about the mirror descent? Put the topic mirror descent then. Right there. So, no, you wrote something, ne? This sentence, this comes under mirror descent. Okay, after this one, no, before this one, if you have a space, write this. Mirror descent. And especially with a pencil, write this with a pencil. Here, you can say cannot apply mirror descent. Okay, online student, did you understand about mirror descent? That clear? Any doubts? So basically, the core concept of the mirror descent is this. Sorry, now here, what did you understand this one? It's telling about magnesium radius. Why it is larger. You have to say downward the group effect is more. That means energy level effect is more than the SNDFF effect across the period effect. That's all. Across the period, it try to decrease. So magnesium try to decrease, but it is not lower as lithium. Okay, not everything. But finish. Boys, finish. Okay, shall we do a few questions from this? Go to the page number 7. Do the first two questions now. Those are from atomic radio. You can see they are asking 2011, 2012. I'll give you a few minutes. Think careful. Try to find an answer. That's the target. Okay. So I explain again how to get the first question. First question right. So put those elements in the squares. Okay. You will see according to the period table, this is how those elements are arranged. And apply your mirror descent. Apply your mirror descent. Okay, so mirror descent will tell you arsenic is larger than selenium, selenium is larger than phosphorus, phosphorus is larger than sulfur. And then you can check the there's another exit here, but only two elements given. Anyway, you can tell carbon is smaller. But if you check the answers, all answers are starting from carbon. That means carbon is anyway small. So that means that first question is checking mirror descent only. If you apply this properly, you will get the answer. And remember, you can't compare carbon and silicon by this time. And it is not needed for get to the answer also. And in the next question, these are the elements how they are arranged. Here's no mirror descent is used. Here you have just understand across the period radius decreases and outward the group width increases. So remember, answer 1 and 2 are the suitable ones. Okay, so answer should be starting from oxygen and finishing with calcium. There are two answers. And we can't take the first answer because It says aluminum, phosphorus is larger than aluminum. It's wrong. Okay. Okay. Now let's go back to our tube. Let's start with ionic radius. Ionic radius. So you know how ions are made. Ne? In last tube we discussed that. If you want to make cations, remove electrons. If you want to make anions, use some electrons. Okay. So like let's read it. Like the size of an atom. The size of ion depends on nuclear charge, the number of electrons it possesses, and the orbitals in which the electrons are residing. Okay, so they have given you three factors. So underline them separately and put 1, 2, 3. Okay. Nuclear charge, number of electrons, and the orbitals in which the electrons reside. The orbitals in which the valence electrons reside. Okay. When a cation is formed from a neutral atom, electrons are removed from the occupied atomic orbitals that are most spatially extended from the nucleus. That we already know. When we want to remove electrons, we remove them from the outermost energy level. That's what it said. When a cation is formed from a neutral atom, electrons are removed from the occupied atomic orbitals that are most spatially extended. Spatially extended means what? Outermost, in difficult words. Spatially extended. By underline and write somewhere outermost. Spatially extended. You can use that name. I'm not home. You can say I'm spatially extended from home now. Is called later. Use it. Nice clear state. Not of you. Spatially extended. I should use it. I'm at a spatially extended class in home. You know? You can use simple words. Okay, right. Outermost. Also, when a cation is formed, the number of electron repulsions is reduced. Okay. What is that? Electrons are repelling from each other. So why didn't we consider that one earlier? We did not. But now they says that decreases. Now that means, yeah. Now think about, let's say. Now let's think about oxygen atom. Just taking random element. Oxygen has 2, 6 configuration according to O levels. 6 electrons in outer energy level. Now, when there are 6 electrons in one energy level, outer energy level, they may try to repel each other. That repelling causes to increase the radius. Same. We cause the repelling try to increase the radius. But let's say now when you ionize it, you remove one electron from the outside. Now in the oxygen plus ion, you have only 7 electrons in the oxygen, not 7, 5 electrons in the outer shell. Now the 5 electron repulsion is lesser than earlier 6 electron repulsion. Okay. And at the same time, nucleus is now a little bit more powerful. It's +1 9. So now nucleus can attract that remaining electrons really well. So that's what they are trying to tell here. Earlier we didn't use that electron repulsion. Why? Because earlier it was dominated by the nuclear charge. Across the period, nuclear charge increases. That's why radius was decreased. So when we are telling that, if I tell about the electron-electron repulsion, then it will be confused. Because across the period, electron-electron repulsion is also increasing. But that haven't affected the ion. That's why we didn't say about it. Now that is clear. Why did we use electron-electron repulsion in atomic radius explanations? Because it was not affecting. Okay, so with a pencil, write that. This factor didn't affect for atomic radius. Electron-electron repulsion didn't affect for across the period atomic radius. Across the period atomic radius. This doesn't affect across the period atomic radius variation. This doesn't affect across the period atomic radius variation. Okay, so now what is the conclusion? Why the cations are, that's it. This doesn't affect across the period atomic radius variation. Okay, now they are telling the cations are smaller than the parent atoms. Who's the parent atom? If it is oxygen atom is the parent atom, cation is oxygen plus. Sodium is the parent atom, sodium plus is the cation, like that. So this is always cations are smaller than parent atom, yes, because of those two factors. So now can you point out those factors? Was hidden inside the paragraph. What is the first factor? Now take sodium for example. Sodium has one electron in the outer energy level. If you remove that electron, it has only two energy levels. It is a reason to lower in the size. And then for oxygen-like element, decreasing electron-electron repulsion is the reason. Now those are the two reasons. Can you see them as two reasons? Lowering energy levels and lowering number of total electrons and minimizing electron-electron repulsion. Okay. So we will put two examples. You need to carefully understand it. Otherwise, it will be complicated, unnecessary. Okay, so I'll ask simple two questions. The two questions are why Na plus is smaller than Na. If I ask that question, what should be your answer? You have to say Na plus is having only three energy levels. Okay, so lowering of energy levels. Two energy levels. You can write the configurations and explain. Sodium 1s2, 2s2, 2p6, PS1 or controllables 2n1. And sodium plus is 1s2, 2s2, 2p6. You have to say, but sodium is having only, sodium plus is having only two energy levels. Only two energy levels. When number of outer shells decrease, number of energy levels size decreases. You have to understand it properly. So what if I ask this question? Why oxygen plus is smaller than oxygen? Then you can't say about the shells. You take oxygen electronic configuration. 1s2, 2s2, 2p4. Oxygen plus electronic configuration 1s2, 2s2, 2p3. Both are having the same number of energy levels. Okay. So what we can say here, we can say electron-electron repulsion. Repulsion decrease. That's the reason. Okay. We can't bring that energy level point here. Anyway, cation is smaller than parent atom. Knowing that will be mostly enough. Maybe really, if they ask to write an explanation, try your best to give the appropriate one. And don't say energy level thing here. That's the biggest mistake you can make. But they have the same energy levels. Yeah. Don't say that, please. Say about the electron-electron repulsion difference. Therefore, atom size shrinks. Online students, did you understand that point? Please raise your hand if you do. Good. We'll go to the next point. Anions. Opposite is true for anions. When electrons are added to an atom, yeah, you need it. I'll explain later. First of all, complete writing. After writing, you can read that anion part and see. Okay, done. Now shall we read? Opposite is true for anions. When electrons are added to an atom to form an anion, the increased electron-electron repulsions cause the electrons to spread out more in the space. Underline that. Increased electron-electron repulsions cause the electrons to spread out more in the space. Okay, for that, an energy level point is not relevant. Okay, you can bring it here, but it's not relevant to that energy level point here. Why? Because normally we are trying to make the noble gas. Now let's say take oxygen. When you are adding electron to oxygen, first it will get 7 electrons. Now 6 electrons are there. No, 2, yeah, 6 electrons there. The A-level aspect. It was 2p4. If you add another electron, it is 2p5. Another one 2p6. After that, normally electrons are not going to be added. 2p6, then it will be s1. Then only that energy level concept is necessary. You can say when energy levels are increasing, radius is further increase. You can tell that. But that point is not relevant for us. So that's why we are sticking to that second point. Electron-electron repulsion is now, increased. Because of that, size increase. That point is enough. And one online student is asking, why do we have 2 points for cation variation? I think you can understand it. Because in sodium and sodium plus, you can see that energy level is not when 3s energy level has disappeared. That doesn't happen in oxygen. That's why we wrote it as 2 points. Okay. It's good to clearly see them separately. Okay, so summary is this. What's the summary? Yeah. Yeah, that means electron repulsion of sodium. Yeah, we can write that there too. But yeah, you can write it there too. But primarily size decreases due to energy level. What is telling is true. And a second point, electron repulsion decreasing is relevant for first answer, first question also. Okay. But for the first answer, you can't write that alone. You have to say about shell too. Understood? Say the both points for that. Can you write that too? The first answer, first question say electron repulsion decreases too. To that term. First question is asking why sodium plus is smaller. Let's say electron repulsion is decreasing. Electron repulsion is decreasing. Electron repulsion is decreasing. Okay, what is the summary? Summary is anions are larger than the parent atoms, cations are smaller than the parent atoms. If you want to explain them, talk about electron repulsion for both. And especially for cations, you can tell about energy level disappearance too. That happens also. Understand them clear. Now the diagram just underneath the paragraphs. Maybe a little bit confusing, but I'll tell. The dark color region. Okay, the dark color region in the first set of diagrams. Okay, is the cation radius. And you can see that they have listed the cation radius from above. If you take lithium, 59 is the cation radius. 157 is the atomic radius. Yes, atomic radius, the one we discussed above. See that lithium is having 157. About every lithium is having 157. And that same value is there here. So that is put two arrows and say 157 is the atomic radius, 59 is the ionic cationic radius. Cationic radius. Now I will give you a small activity to do. Use your knowledge and practice and see. Can we apply mirror descent for cation radius and radii and anion radius? Check and tell me. You remember the mirror descent? Can we apply that mirror descent trick for anions and cations also? Now select 4 cations. Example: lithium plus, beryllium plus, sodium plus, and beryllium 2 plus, sodium plus, and magnesium 2 plus. Apply that tensor. Is there any place we can't apply that to? Or all the all the places are possible. In anion side, there is no problem. Eh? In anion side, there is no problem. So put a curly bracket or something. Say for anions, the listed anions, so they will only ask from this link. You can say mirror descent is applicable. Mirror descent is applicable for anions. for any set of anions. That's also useful, Lamai. Now, this isn't what I'm gonna tell you. Now, if they ask you whether Cl minus or O2 minus is larger, you get confused because Cl minus is in the lower period, having minus one charge. If you go to O2 minus, it is in the upper period, having minus two charge. Having the minus charge more will help to increase the size. So they don't get confused. Okay, oxygen hasn't become larger. O2 minus hasn't become larger than yeah, Cl minus. You think no? Then you may get lost there. They get confused and go with the wrong answer. So that's why the mineral descent is important. Not only for atomic radii, we can bring it to ionic radii also. Now we are not worrying about any anion from now on. You put mineral descent and see. Again, that means what in simple words, this point means downward group variation is more powerful than the crystal variation. Downward group radiation means energy level effect. Energy level effect is more powerful than the charge effect because of the negative charge. Size is increasing. Then that effect, energy level effect has become more dominant. Shall I write that too? You can chill or something. Near that point you wrong. You can write energy level effect is more powerful than negative charge effect. Simple. Energy level effect is more powerful than negative charge effect. Now apply that one for our cations. See whether in which places it falls up. You take lithium 59, 27, 102, 72. That is okay. Lithium, beryllium, sodium, magnesium, okay. Then sodium, magnesium, potassium, calcium, it is not, it is breaking. Huh? Then potassium, calcium, rubidium, strontium, again it is breaking. No, it is holding. 148, 126, 138. Ah, no, it's again breaking. Can you see? If you want to compare in S block, only that rule holds up to the first four. Okay? Yes. That's the problem. What about the other one? Magnesium, aluminum, calcium, germanium. Same problem. Yeah, same problem. Yeah, same problem. Huh? N shape. N shape. N shape. Yeah. You want to put a shape. Yeah. Yeah. But you may be confused with N and Z. So I'm not going to tell you. Okay? When you are studying, you can what you can put it. So what we now anyway they will not be asking. You know what should we do? Let's say for cations, that rule is only applicable for where? For the yeah, put another red color square or something around lithium, beryllium, sodium, magnesium, and say mirror descent is applied only here. Look at that also, it's wonderful. For anion side, it is applicable everywhere. But in cation side, only that four pairs, the first four pairs are applicable. Don't worry about the exams. With the answers they are giving you, you can eliminate the necessary ones and go to the answer. Okay, on naturals, that clear the one I said now. See your problems. Okay, Sena, now did you understand why there are two reasons? This was an older question you asked. Very clear with that. Energy level effect is more Sundra, energy level effect is more powerful than negative charge effect. So let's say energy level is more effect is more powerful than negative charge effect. That's the sentence I told you. Yeah. Then negative charge effect. Okay. Negative charge. Okay. Now let's go to the next page. Oh, ions carrying same charge, positive or negative charge. Ionic radius increases as we move down a column in a periodic table. That means similar to atomic radius. Downward the group atomic radius was increasing. They says in the same way downward the group cationic radius and anionic radius increases. That means sodium plus is larger than lithium plus. We can understand that. Energy level effect. And in other words, the principal quantum number of outermost occupied orbital of an ion increases, the radius of the ion increases. So no need to highlight that. That's something we can understand. And what is this new word? Is it a new word actually? You had this word in earlier too. Isoelectronic series. Isoelectronic means, yeah, it is defined. Don't underline that. The groups of ions or atoms containing the same number of electrons. Containing the same number of electrons. For example, each ion atom in the isoelectronic series OF, O2 minus, F minus, neon, sodium, magnesium has the total number of 10 electrons. In any isoelectronic series, the nuclear charge increases with increasing atomic number in the series. Yeah, it's true. Oxygen is atomic number 2. Chlorine 9. No, atomic number 8. Chlorine 9. Neon 10, sodium 11, and magnesium 12. So it increases. As the atomic number increases, nuclear charge Z. Then last week we used the word Z, no? That Z. That Z is also increased. Okay. Because the number of electrons remain constant, the ionic radius decreases with the increasing nuclear charge. As the electrons are more strongly attracted to the nucleus. Underline that last sentence. Highlight that last sentence. That is the one explains why isoelectronic series radii are arranged in that. Because the number of electrons remain constant, telling it nicely. Because the number of electrons remain constant, ionic radius decreases with the increasing nuclear charge, as the electrons are more strongly attracted to the nucleus. A good explanation. Okay. And then you can see a handwritten note at the end of the page. It's actually a photo of a whiteboard note tagging. Photo you can edit. And so it contains even a tiny important point you need to remember. Right? So the things we discussed now is basically addressing about how generally across the downward group ionic radius changing and how to apply and how where not to apply is mirrored said. And then isoelectronic, but there are more points. Okay, shall we go through them? Look at the first point. Ionic radii increases down the group. Is that correct? Yes. Cations are smaller than parent atoms, and anions are larger than parent. We have a good reason for that also. Electron repulsion, electron attraction, and electron repulsion increasing, decreasing. The one is shares. We have a good explanation for that. And then isoelectronic series. Okay, isoelectronic series. Look at the location of neon. Neon sodium plus radius is greater than neon. Please check that one from our table. Sodium plus radius is 102. What is the neon radius? Neon radius you have to go to the above table. It is 100 and so it is 70. That's a nice to know point. Neon radius is smaller than sodium plus. We might suspect that neon sodium is basically having sodium plus is basically having neon electrons. Sodium plus is neon. Sodium plus is having the same number of electrons as neon. Neon is having 10 electrons. Sodium plus is also having 10 electrons. And sodium plus is having plus 1 charge also. So we might suspect now okay, sodium is having more nuclear attraction. We can say more, what do you say, more nuclear charge. And therefore sodium should be smaller. And then we might think. But actually it hasn't happened. Okay. So sodium radius is slightly higher, not slightly, considerably higher than neon radius. Okay, considerably higher than neon radius. And then the next thing, mirror descent. It is applicable for sodium, magnesium, and those things. And I said it cannot be applied to those. And group 1 atoms on those. Now, the last point in that left side is the first one you need to see newly. Group 1 atoms is larger than anions of the above period. Group 1 atoms are larger than anions of the above period. So group 1 means potassium. Okay, see, potassium is larger than sulfide and chloride. See whether it is correct. Potassium size is 235 atom size, and sulfide and chloride 184, 181. And see whether it is correct for sodium. 191 is larger than 140 and 146, 140, 131. Yeah. Now what we expect is anion to be larger. Anion should be larger. We expect it to be. But this point proves you anions are large, okay, no problem. But it is not large like the next period first element. Next period first element is the biggest one. That point may be valuable sometimes, not sure. Still they are not asking. And 1 year they have asked one of the extra points. 1 year. But if the next year is there, 2028 there, I'm surely without study. They might be asking this intern test and everything. A-level sitting, they are not going to go that much deep. But anyway, that concept is okay to understand. Anion size is larger, okay, but next period, first element, atomic radius, sodium, potassium, those are larger than previous anions. Okay, that point is clear. Understand by looking at the values. Okay, we are not supposed to find reasons. You want a reason, you can say energy level effect is more powerful. Sodium and potassium, sodium are having additional energy levels. That's all. And second period anions are larger than fourth period cations. And third period anions are larger than fifth period cations. So that is telling something else. Okay. See, N3 minus, O2 minus, F minus are larger. And they are larger than potassium, calcium also. Potassium, calcium cations also. Potassium cation 138. Calcium cation is 100. What is the point again? Fourth period cations. No, that's correct. I am the one who knows. Second period anions, nitrogen, oxygen are larger than third period, fourth period cations. F minus is 131. That is that applicable, but anyway, to the next period it is applicable. S2 minus Cl minus are larger than Rb plus and Sr plus. SR2 plus. Rb plus and Sr2. Okay, so that means electron repulsion is more powerful than energy level effect. Yeah, because anyway, if you take potassium plus, it is having 3 energy levels. Okay? Potassium plus is having 3 energy levels, and N3 minus is having 2 energy levels. Okay? But energy level effect, the electron repulsion has become more dominant there. But in earlier one, what is the dominant factor? Energy level is that potassium is larger than S2 minus Cl minus. So those 2 points are not asked yet. The level exam. I haven't seen any. I have seen only one. Same structure is a question, small sentence, 3-mark question out of 100 mark of that structure. That means if you have to divide that 3 marks by 20, right? A-level mark. So it's a very small mark, fraction of mark. Is being asked from the 2 points that I told you now. But the next point is somewhat common. Next 2. That is easy to understand also. What are they? Same period ions are larger than their atoms. And that means what? F3 minus O2 minus F minus are larger than N. That means the important thing is this number. F minus is greater than nitrogen. F minus is larger than nitrogen. Okay? Now we know F minus is larger than F, but it's not enough. You have to say F minus is larger than nitrogen. Nitrogen is biggest one, no? Of that 3 elements. And then same period cations are smaller than their atoms. That means sodium plus is smaller than aluminium. The important thing. So highlight those 2, the last 2 only. Okay, highlight the last 2 only. Same period ions are larger than their atoms, and same period cations are smaller than their atoms. Okay, now to practice everything. Yeah, anyway, I'm going to give you a small break also because of that question. Question number 3 and 4 you can do it at the interval. Now try the question number 5. Try the question number 5. Decreasing order of the radii. Decreasing order of the radii. Question number 5. It is from new syllabus paper. Okay, what is the answer? Yeah. Now for those and for anions, apply mirror descent. Right? You don't have to worry about mirror descent for anions. Can be applied for any anion set. Right? And apply it. And find out which one is the largest and which one is the smallest. Now in this question, they have made it difficult by introducing elements also, atoms also. But don't worry, according to the last 2 points we highlighted, the addition to remember, we know that atoms are smaller than their anions. Okay? That means basically F minus is larger than oxygen. F minus is larger than nitrogen. Yeah. So what is the answer? Those who take answer one. One. One is that the answer? Yeah, answer one. I told you who is correct. Sorry. Answer one. I didn't read the last. Last part is wrongly the answer two. But answer two says F minus is larger than oxygen. Not oxygen is the larger one. Okay? See it. So answer is answer one. Good. Online students, to take the answer one. And I see hand raise. Okay, write a good review. Write a good review now. Few students has mixed that. In physical class also same thing. You might selected other answers. Now, first of all, I'll give you a review for that one. Sulfide, chloride, oxide, and fluoride. The mirror descent. Okay, mirror descent is true. Why? Because the downward group effect, the energy level effect is more powerful than the charging. So S2 minus is the largest, then Cl minus, then O minus, then F minus. And then go to that last point we highlighted in our handwritten notes. It says anions N3 minus, O2 minus, and F minus are larger than nitrogen, oxygen, fluorine. Take this point and add it here. You can say now F minus is larger than oxygen and fluorine. That's how answer one comes. Clear? Now is that clear online students? You all understood? Okay, write a good review near that. Now, we'll take a small review. Let's start around 6:20 and go through these questions. I'm giving you some more time for you to try these remaining questions. Now, it's not like ionization. Ionization was not easy than this. Particular easy. Ionization. You get the graph, you will get the answer, something like that. But in a maker, there's no graph. You have a table, obviously you can't remember those values. And you have small statements, is it, and special facts like that. So there's a challenge. So try all the questions, the remaining ones. We'll discuss them. Only this page is there, the page. Radius. Okay, online students, complete them. We'll take a small break. If you have any further doubts, send them, I'll answer you guys. The remaining MCQs. I think we discussed the fifth one, no? So we have to do fourth and third and fourth. Okay, look at the third MCQ. Increasing order of the atomic radii of, now it is combined again, boron, oxygen, sulfur, sulfide, and chlorine. Okay. Right. Now, first of all, see whether what are the locations of these elements. Boron is somewhere here, carbon, nitrogen, oxygen is somewhere here in the periodic table. You can use your O-level periodic table for these questions, no issue. Then sulfur is the below element and chlorine is somewhere. Sulfide, keep it out from the picture because is the biggest one, sulfur, from the whole set. And then how to compare them? These elements. You know, from this variation, oxygen, boron is larger than oxygen. And from this one, you know, sulfur is larger than chlorine. But when you want to compare oxygen and chlorine, you have to go with our mirror, is it? And from that, you know, chlorine is larger than oxygen. So then you can finally put them everything, together and say, are there some increasing one? Increasing order, no? So from the smallest one is oxygen, then boron. Again, we face a small trouble. Okay, when comparing boron. So let's skip boron and write oxygen, chlorine, sulfur, and then sulfide. So now the problem is where we will place boron. I think in answers we don't need that. That's the way they ask questions. So without knowing exact location of boron, we can find the answer. Now let's see that one. Sulfide is the largest, so there's only two answers. And then in both, boron is larger than oxygen, so that is properly represented the third answer. Okay, those who got answer 3, good, good, good. Answer 3. No, what did you select? First one. You mixed up with boron and oxygen. Across the period, radius will what? Decreases. Okay. Now, okay, you underline that and put a statement there. Across the period, it decreases. Then your mistake is correct. Okay, online students, how many of you got answer 3? Good. No. You have sent me, good. Okay. Then fourth question. Say now you have asked about the fourth question. We'll see. Which of the following statements regarding sizes of ions formed by sp blocks elements is false? First one, cations are always smaller than their neutral atoms. That is correct. Anions are always larger than their neutral or parent atoms. That is also correct. The size of cations decreases from left to right. Size of cations decreases from left to right. That means sodium, magnesium, aluminum. Left to right means across the period. Is that correct? Yes, no. So write that one. Sodium plus is larger. Sodium plus is larger. Then magnesium 2 plus. Then aluminum 3 plus. So get some example and think. Don't just without example, don't try to get the answer. And the next one, size of anions increases from left to right across the period. So 9 minus, O2 minus, and F minus. The size of anions is not increasing. It also decreases. And that is the wrong answer. Fourth one is online students, how many of you got fourth answer as wrong? That's the incorrect or false state. Yeah. Give an example. From the examples, we can say it is wrong. That's the only way get the answer. Last one should be correct. Anions formed by elements of the second period are larger than cations formed by the elements of third period. So they are talking about isoelectronic ions. So give that one. If you connected these two, you can say N3 minus, O2 minus, F minus are larger than sodium plus, magnesium 2 plus, and aluminum 3 plus. Okay. You can see as the number of protons increases, as the number of, like this source, number of protons increases, or is it increases, size or radius decrease. Size or radius decrease. Oh, then go to the sixth question. Correct order of increasing radii. Correct order of increasing radii. Beryllium 2 plus, magnesium 2 plus, sodium plus. This is, we need to use, is it ne? First answer is it correct? Beryllium 2 plus, beryllium, magnesium, then you have sodium. So if you apply mirror set, tells you exactly in that way, that is correct. And then second one, O2 minus, F minus, and so I think the first one is the answer. Okay, now correct them, others. What are the correct increasing orders of other three? Increasing orders, right? So say O2 minus and N3 minus. Second answer is the corrected version. Third answer, sorry, I wrote for the third term. For the second answer, the corrected version is these are it is also related to isoelectronic number. Isoelectronics are right full order. P3 minus is larger than S2 minus, and it is larger than Cl minus, and this is larger than potassium plus, calcium plus, calcium 2 plus, and scandium 3 plus. Scandium is the D of first element. So in this order, you can see how the calcium, sorry, potassium, sulfur, and yeah, potassium, calcium, sulfur. Can see that isoelectric series. Correct? Isoelectric series. And then fourth one, uh, oxygen O2 minus, S2 minus, and then you have the arsenic. No? Because arsenic is larger than, you can say like arsenic 3 plus is larger than P3 minus. So S2 minus is smaller than P3 minus. You can write it like this. Right? P3 minus, but bracket, and say it is arsenic 3 plus is larger than that. That way it's clear. They haven't give you P3 minus, but P3 minus is the middle one. Okay? Boys, you got the idea? You had it. Okay, so these are the corrected both versions for other wrong answers. Okay, online students, hope you understand. Say now why you are raising hand. Is there a problem? Question you have? Ask for it. There are any doubt, please ask. Right then, question number 7. Increasing order of the ionic radii of the following species: sodium, magnesium, potassium, calcium, sodium and magnesium 2 plus. Yeah, what is the smaller one? Can we eliminate the answers? First one you can eliminate, no? Why first one can be eliminated? It says magnesium is larger than sodium. Underline that and say wrong. Let's try that method. Sodium and magnesium, underline that and say wrong. Because of this, it is wrong. There are other mistakes. Okay, sodium, potassium, calcium is also wrong in the first answer. And if you go to the second answer, it says magnesium 2 plus is bigger. Again, it is wrong. Then if you go to the third answer is okay, right? Third answer is okay. Potassium, calcium, third answer. Calcium is larger. We'll see. We'll go to the next one next. Fourth one says sodium plus is bigger. But fourth one says sodium is smaller than magnesium atom. That is wrong. In the fifth answer, it says fifth answer and third answer both are identical. No. Third answer is wrong. Neither. I forgot. Sodium is larger than right, magnesium 2 plus. So third answer is wrong. So go with the fifth one. This is the correct answer. Okay, online students. Okay, go to the question number 8. Select the answer that has arranged the given entities in the ascending order of their size. The ascending order of their size. Entities in the ascending order of their size. Nitrogen, oxygen, fluorine, not the ascending order, right? The correct way. It is fluorine, oxygen, nitrogen. Is fluorine, oxygen, nitrogen. Second one is again wrong. It should be in the other way. Fluorine, fluoride, oxide, nitride. Second one is also you have to change. Fluoride, oxide, nitride. Nitride is the large. Because why it is larger? You can say it has more electrons. More electrons than the proton. It's a nuclear charge. You can say this is a nuclear charge. That's why N3 minus is larger. And sodium plus, magnesium 2 plus, and aluminium 3 plus. That is also wrong. It should be again in the opposite order. Okay, aluminium 3 plus is the smallest. Okay, sodium plus, neon, and F minus. Sodium plus, neon, and F minus. Sodium plus is larger than neon. So it is also wrong. According to our special point. See, this is a term-based question or model question. In those questions, they are expecting that. Okay, so then change, write the correct order, neon, sodium plus, and F minus. That is also wrong. Then fifth one should be correct. Let's check. Strontium, gallium, germanium. Where these elements are? Go to the period table and see. Strontium is in the strontium, gallium and germanium are in the above period. So it's not the ascending order. In that also wrong. There's no answer for this. Yeah. Size can radius come. Radius. Fourth one, according to the special point, we can't take neither. Look at the special point, the handwritten. It says sodium plus is bigger than neon. මෙහෙමයි. let's say this came to our exam. Let's say this came to our A-level exam. And now you can see, don't get scared. You can see there is no answer, but we can't leave it blank. Then we will have no mark. So what is the best answer? Fourth. Best answer is fourth time because it is an extra point. And sometimes professor might have think, okay, this is not needed for students. It might have think in another way. So we have to mark fourth one. That is the best answer here. Okay, so mark it, but say because other answers are totally wrong. This is the but accepted one. And without knowing the values, this is the answer normally a student going to pick. So we also have to pick that answer. Okay, now question number 9. Which of the following electronic configurations represent the element with the largest atomic radius? Now, electronic configuration and period property both are connected here. You remember electronic configuration was connected with quantum numbers. Like this is also connected to a periodic configuration radius. So, what do you think? Which one has the largest? First one. Fifth one. First one. Fifth one. You are selecting fifth one because first one you are just designing more electrons. Across the period, left to right, size decreases. Isn't it? Okay, now write the element in front of each configuration. That way also you can find the answer. Now first element is what? Fluorine. Second element 1:2:2 beryllium. Third element neon. Fourth element magnesium. Fifth element silicon. 3:3p2. Carbon is 2:2p. Silicon. Okay, now compare. Is it silicon or is it magnesium? Magnesium is the largest. You should consider the now there are only 3 elements in the third period. What are they? Fluorine, silicon, and magnesium. When you compare fluorine, silicon, and magnesium is the largest. Isn't it? What will the answer for? Energy levels increases, radius increases. Fifth one, it is silicon across the period. Now silicon and magnesium both are having 3 energy levels. But in magnesium, but in silicon, same energy level electrons are more. Electrons are filled to same energy levels. So you remember across the period radius decreases as nuclear charge steadily increases. So silicon is having more nuclear charge than magnesium. That's why silicon is smaller. Can you understand? Right near your answer. If you selected answer 5, you can write silicon has more nuclear charge than magnesium. Someone selected answer 5 right near that. Silicon has more nuclear charge than magnesium. Therefore, size is low. Answer is magnesium, answer 4. That was a good question. Eh? First one, why first one is strong? It is fluorine. Fluorine has even more nuclear charge than silicon. So fluorine will be smaller than silicon. Remember, they are in the same period. Think in that way. Magnesium, in your angle, magnesium, silicon, fluorine. This way, radius decreases. Ne? Okay, 10th question, last one. The correct order of decreasing radius. Correct order of decreasing radius. S2 minus, Cl minus, K plus, and calcium 2 plus. It's electronic. Okay, click on it. isoelectron. They all have the same number of electrons. Write that on underline all four and say these are isoelectronic to argon. These are isoelectronic to argon. These are isoelectronic to argon. So in isoelectronic series, you can write that. I wrote it somewhere. I think P3 minus anything at the top. P3 minus S2 minus. Write that order once again. Okay, so what is the answer? First one. Good. Okay, then Lamai, we will discuss about today electronegativity. Because electron gain energy, if you go to that part, you will find there are 3 pages, and honestly, electron gain energy is one of the most important things in unit 1. Again, then, as a teacher, I remember what are the difficult areas for students. And first thing is hydrogen emission spectrum. People are struggling with that. So I don't know whether you are okay with that. So we have to study and see whether it is okay. So get started now. And from next week, this lesson is done. So I might keep the test in next week or in the afterward. So small one and the one number. I'm not going to tell when. Don't you study and come. It is given just for me, for having some idea about your study patterns and method. That's it. I will keep a proper exam after finishing unit 2, 3, 1, 2, 3 units. Evaluation test 1. That's the big test. Small test. Okay. So study unit 1 only. Unit 1 only. Okay. We did some calculation parts. I'm going to ask them. So study. Okay. And we are going to discuss that paper also. Maybe next week or the after. Don't know. We'll see. Yeah, you absent. You are joining online. Sir, can I have the link? No. No. Never. Denying. Okay. Recording the net. May. It is a meme. You are having, let's say, some kind of a illness or something, neither. Severe headache. Can't lift the head. Then you can stay home and neither. You can actually rest. No, you can't participate online also. You have to stay like this and stay at the screen. So I'm giving only one recording per month. And that's a policy we implemented from this year. Last year's 26, 27 batches. 26 batch it was okay because I started to give organic recordings in the middle of their years. But for 27 batch, I started from their very first month. They need the recording. I'm not going to ask anything, just give it. But now I see the results of that. Those the students who are requesting recordings all the time, now they can't do anything. And they don't come to the test seat, some students. Again, a recording, you are giving up that one, okay? Then you are not going to watch that recording also. Then it get expired within 2 days, 3 days again. 1 week again. After that, it get expired. Expired means I'm deleting it because storage is 10 GB. So after that, you are not again requesting it. So that happened for 27. So then they discussed that actually happened in the Nugeboda principal, the sir was of our institute. He told that don't give recordings, give only one. If they need more than one, they need to pay extra. in 27 batch තමයි මාර case එක කියන්නේ දැන් when we check the attendance for one day, there are like 70-75 students are coming for one day. But at the end of the month, there are 90-95 students has paid for us. ඒ කියන්නේ අර 20ක් විතර ඉන්නවා එක දවසයි එන්නේ. once a month වගේ ඇවිල්ලා ඉතුරු ටික recording එක. Then those people are not going to get good days. Then when someone asks, where did you went for chemistry? When they say my name, okay. So that's why as a policy we implemented that there. So then we can apply the same rule here. Right? Only one report. If it is a bad thing, sometimes you get, in chicken box and you have to stay for 2 weeks again. But a report, it is something. Unnecessarily absent. And the bad thing is this now, when we are learning as you, I was not a very bright student. I got good results for levels, but I'm not a very meter candidate. I'm not like someone like that. It's normal, ordinary student, just like you. But we didn't cut classes. And we didn't miss that because at that time when we are writing A levels 2013-14, there was no recordings. If I absent, I was absent, no note. But my friends are also not writing a note there. I'm the only one who's writing a note there. Okay, so I'm not going to get absent. But I don't have a note to study. Sometimes when we got sick, couldn't go to the class, Monday was going to one day, and there's no recording, and can't understand anything told in the next day. Not for like chemistry and all that, but physics and theory, but the first day is related to the second day. It's very difficult to understand. Biology is also fine. Physics, chemistry, physical chemistry is also difficult like that. You would need the first day to understand the second. Organic chemistry is very, very difficult. Again, organic, let's say organic we are doing for like 4 months again. Second month, first day theories are needed to the last day theories of the fourth month. It's a long lesson. Easy, but interconnected. If you missed one day, if you didn't study, so don't get absent. Try to come to the physical class. Right? And we started that there. I told the 28 batch and gave them nobody's decision. And for you also, and I have to get somewhere else, I think it will be for the betterment of everyone. Right? And you need your results. We have just teaching career start like nearly like 10 years. So this is the blooming period of ours because we got enough experience to show our results. And results in this blooming period, if you didn't show results, then my era is also fading within like next 5 years. You're not going to find me. But if you show results, then I can continue my career for another 15 years. Now, decision is done on one report. Okay, after that, no. Online students, for you also the same. Anyway, I'm getting you recording to the group, but try to come to the live class. But you know how some students are watching recordings? I also know that one recently. You can increase the speed, no? So I am doing it for like 3 hours. They stay home and they think, okay, I'm going to do something useful. Game match. They increase the speed up to 1.5, 1.7. Don't understand anything. My text time, I usually speak fast. Our speed them. If they will not understand anything. See how stupid they are. Right? Right now you haven't missed anything. The first lesson is easy. Again, difficult right? So the difficult thing is emission spectrum and electron gain energy. honestly. තමයි ළමයින්ට බෑ. Right? I have seen for like my previous years, those two are the lessons students are struggling. Emission spectrum and electron gain energy. So electron gain energy we will discuss separately next. And then now for that those difficult topics also I'm giving you some extra recordings. Remember for emission spectrum we did a full revision online. If you forgot that, you can go and watch that. No issue. Those will be available for until you write for exam. Another thing. Now let's say after a few months, you want to revise unit 1 again, and request recordings, no problem. එහෙම දෙනවා. ඔයාලට අර month එකේ අර absent scene එක තමයි මේ I'm trying to break. Okay? Oh. Right now, what we're doing? How this one? What is this? Electron gain energy we're going to discuss next day as I suggested. Now there's one more periodic property remaining. Shall we go there? Because they are in your O levels. What is that? Electronegativity. Electron is a small discussion. We'll do the questions. Electronegativity. Okay, it is defined as the ability of an atom in a molecule to attract electrons to itself. The greater an atom's electronegativity, the greater stability, so greater its ability to attract electrons. Okay, it is defined as the ability of an atom in a molecule to attract electrons to itself. Greater an atom's ability electronegativity, its ability to attract electrons is higher. Okay, I'll give you one diagram for this one. Okay, I'll give you a small diagram for this one. Please draw that near that paragraph. It is the ability to attract electrons. So now if you take HF and HCl, okay. So hydrogen is common. You know this halogen. Now you know those words. Halogens are the group 17 elements. Chlorine, bromine, iodine, like that. So these halogens are more electronegative than hydrogen. You know, fluorine is more electronegative. You know, more electronegative. It is more electronegative. And if you consider fluorine and chlorine is more electronegative than chlorine. So here you can put a diagram like this. Fluorine attract electrons more. Can you understand that? So like that, if is showing the ability to attract these bond electrons. So now one dash represents 2 electrons. This dash represents 2 electrons, 2 bonded electrons. So those 2 electrons are attracted more towards the fluorine and chlorine. When you compare fluorine, it is attracted more towards the fluorine because it is more electronegative. Now you understand electronegativity, ability to attract electrons, likeness towards the electrons. But it is defined for cases like bonded cases. And there must be a bond to attract electrons. Understood me? Now what is happening to the electronegativity downward the route? That ability, as you can see here, that ability is decreasing. Why? Ability to attract. So attract word is there. So then who's attracting these electrons? Nucleus. So electrons are attracted by the nucleus of the chlorine like that. So it is nuclear attraction. Okay. So what is happening to the nuclear attraction downward the route? It decreases. Yes. Why? Because of the effect of radius. As the radius increases, nuclear attraction decreases. Right? So fluorine, bromine, iodine attraction decreases, so electronegativity decreases. Ability to attract electrons become weak. Now you can understand it here. Chlorine is having lesser nuclear attraction than fluorine. Cl has lesser nuclear attraction than fluorine. Therefore, Cl can say electronegativity. Electronegativity of chlorine is lower than electronegativity of fluorine. Understood? So downward group variation is explained by nuclear attraction. So across the period, what is happening? Nuclear attraction increases. So with that, electronegativity is also increasing. Okay. You consider NH3, water, and HF. Okay. Fluorine is more electronegative than any of these. Then oxygen, and then nitrogen, 1F. Why? Because nitrogen, oxygen, fluorine across the period. Nitrogen, oxygen, fluorine across the period, electronegativity increases. Shall you write these small notes now? It will help you understand without reading the paragraph. Across the period, electronegativity increases as the nuclear attraction increases. Nuclear attraction increase. Okay, online students, did you understand this about electronegativity, this explanation? Afterwards, you'll go and see the helium gas is greater electronegativity than fluorine. Who says? In our table, helium. Okay, if you finish it, we can go through the paragraph. So simply it is the ability of an atom in a molecule to attract electrons to itself. Remember that molecule atom, which should be always in a bond. Okay, the American chemist Linus Pauling developed the first and most widely used electronegativity scale, which is known as Pauling scale, which you had 4 levels. There is an increase in electronegativity. You didn't have Pauling standard, you had given these numbers. Yes, there was a small table at the right side upper corner. No?
The table.
Yeah, the table. In the table, they give numbers. Ne? Yeah, below that, you have ionization energy. Okay. And then, yeah, generally, there is an increase in electronegativity from left to right across a period in the periodic table, with some exceptions, especially in the transition metals. We are not going to discuss those exceptions, don't worry. And electronegativity decreases with increasing atomic number, the group. That means downward the group. Shall we underline that and say downward the group? Increasing atomic number means downward the group. Otherwise, it will be a bit confusing. Increasing atomic number means downward. Increasing atomic number means downward. Noble gases too have very small but non-zero electronegativity according to the Pauling scale. Very small but non-zero. Yeah, non-zero means they don't have, they are not zero electronegativity. They have some ability. But noble gases, Pauling found a value, but when that value is actually useless. Why? Because they are not making any actual bonds. So we don't consider that value. So even you can see in our table, it is not given. Noble gases are not there. Okay, so you can write that one. Write this sentence. Electronegativities of noble gases not necessary. Not necessary. Because they don't form, most of them are not forming actual bonds. Electronegativities of noble gases are not necessary. Because most of them are not making actual bonds. Because most of them are not making actual bonds. And there is no purpose no, for that number. Then you'll only confuse you. So don't think about that number.
Noble gases make bonds.
Noble gases. Yeah, there's only two noble gases that can make bonds. Not hydrogen, helium. Helium, neon. Helium, neon, argon. What's the next element? Krypton. After krypton, you have xenon. Xenon is making bonds. That is also with oxygen and fluorine. With more electronegative other elements. Otherwise, xenon is not going to make any bonds with any elements. That will be discussed later. Don't worry about it. Yeah.
Most of them are making actual bonds.
Actual bonds. Because most of them are not making actual bonds. Only xenon makes bonds with oxygen and fluorine. That's it. Okay. In molecules, the difference between electronegativities of two elements forming a bond will determine ionic or covalent nature of the bond. That's true. You can write if electronegativity difference is higher by this system. If the electronegativity difference is higher, the bond will become ionic. The bond will become ionic. The electronegativity difference is higher. The bond will become ionic. The bond will become ionic. Bond will become ionic. Okay, then can you see an order? Chlorine, oxygen, chlorine, nitrogen, bromine, iodine, sulfur, carbon, phosphorus, and hydrogen. You need to memorize that. That's the only thing I'm asking. Other things are not that important. Memorize that order. FOCLN. Brisk. FOCLN brisk. pH. Make something. You can remember FOCLN. Write a small poem thing. Try to remember. Like you remembered period table. No else. Okay. Knowing that has some uses. That's why. Take some time. Slowly try to remember. Memory will go to your permanent memory as you use it in questions. So now you will remember it some according to some method today, let's say. So it may be forgotten in the next day. It's fine. But remember the way you study. If it is a poem or something you are making up, write it with a pencil and keep it. So when you are studying, when you are doing questions again and again, you can use it again and again. So by the time you will remember. And there's no fixed definite method to study things, especially things like that. It's very hard to make a poem most. F4L, F4CLN. Huh?
How did you prepare?
I just remember. That's why I said I'm doing questions. I back then, but I remember now it's changed a little bit. That's it. I'm not going to tell how I remember. Now the two places I had to change according to your new syllabus. Two elements were changed. So if you make a good poem or something, you can share that with. Then I can teach that to next batch. Okay. But
He was pretty close.
because anyway now we are doing questions. Welcome. Okay, so now go. You can try the questions till others come. Okay, online students, try to remember this order. And here you have the actual values only, no need to remember values for it. Just remember this order. Now you can see chlorine and nitrogen are having same values, but remember chlorine first. Okay, here also carbon, iodine sulfur carbon are having the same values, but remember iodine, sulfur, carbon in that exact order. Okay, I'm telling them for a reason, you will understand that later. Okay, now shall we try these questions in the page 40? Oops, Atif, you, Atif, Atif, maybe, yeah, we see it. The mother called me and sorry, Afia. Ah, okay. The brother Afia's Shapras. The brother will pick up. Who's Apia? Your brother will come to pick you up. Okay. Your mother will come with you. Usually, how do you travel? Right. Lama, shall we try these questions? In page 14, you have two questions about electronegativity. Okay, right now I was telling our students, we have very little to discuss here about electronegativity. And the reason is electronegativity based on bonds. You don't know anything about more new things, but not the A-level stuff yet. So in bonding lesson, we will take this electronegativity topic again and discuss. So there we will go into more details. And for example, it's like this now, nitrogen according to Pauling scale, it has the value 3.0, but that value is not a fixed value. It changes depending on the nitrogen environment. Nitrogen environment means how many bonds nitrogen make, what atoms it will make bonds, depending on those characteristics, its ability to attract electrons changes. So we're going to discuss that once we learn about bonds. Okay, so right now it's a small discussion. What you need to know, what is electronegativity, ability to attract electrons, and that ability decreases downward flow. And across the period it increases. And remember that order. FOCLN, BRI, SC, BH. Good. Right now, what is the answer for the first one? Which of the following gives the correct increasing order of the electronegativity? Which one gives the correct increasing order? And for the period table, indium, tin, nitrogen, and oxygen. Nitrogen, oxygen part is okay. Indium and tin. Indium is clear. Which period? Use the normal period table. Indium. It's in the group 30. Tin is in the group 40. Same period. And then across the period, radius electron increases. So that order is correct. Answer 3. Then shall we arrange others in proper order? Answer 1. It's the other. Beryllium is the lowest. Beryllium, selenium, sulfur, and oxygen. Write the first answer. Beryllium, selenium, sulfur, and oxygen. That's the increasing order. Okay, they have given me the decreasing. Look at the second answer. That also in the other way. Selenium, phosphorus, sulfur, chloride. Selenium, phosphorus, sulfur, chloride. That's the proper one. Third one is correct. Fourth one. Anyway, it's difficult to arrange it somehow. Selenium or silicon? Value? Selenium or silicon? Is it silicon? You have the actual values, now go to the actual values and see. Selenium. Selenium, eh? Yeah. Then selenium 2.4. Phosphorus 2.1. Okay, then write the correct order. What will order? Carbon. Sorry. Tin, eh? Tin is the lowest. Tin is the lowest one. Then P. Write this order. SN. I'm telling about the fourth answer. Sorry, in the fourth answer you don't have SF, sorry. Silicon. Then write phosphorus, silicon, phosphorus, carbon, selenium. Anyway, it's not needed, okay? You already found the answer. Writing. What is the answer for the last one? Can we use our order? Right there. F is the highest, then oxygen, then chlorine, then nitrogen, chlorine, oxygen, fluorine. Nitrogen, chlorine, oxygen, fluorine. Okay, nitrogen is the lowest. Then chlorine, NCl5. Both are having same values, but write nitrogen first. You'll understand why later. Nitrogen, chlorine, oxygen, and fluorine. Okay, nitrogen is the lowest, then chlorine, then oxygen, then fluorine. Good, good. Anyway, answer is answer 3. Next one. Correct order of electronegativity. Now, cesium, rubidium, sodium. Use the last page period table. Right? Cesium, rubidium, sodium, they are in the first group. Okay, downward the group, electronegativity decreases. So this is wrong. Cesium is the lowest element. Cesium should have the lowest electronegativity. So can you write it again? Sodium is the highest. Then rubidium, then cesium is the lowest. Okay, use this table. Use this table. And find the answer. If in the exam, you don't have the values, and don't need the values. Without values, find the answer. Okay? Right. So A is wrong. B, lithium, beryllium, boron. That's correct. Across the period increases. Okay. Third one, carbon, nitrogen oxide. That is also correct. Across the period increases. Like that. No, don't look at the values. Across the period, it increases. Fluorine, fluorine, bromine. That's wrong. Fluorine is the highest. Fluorine, then chlorine, finally, bromine. Is that clear? Okay. So now listen. You have some homeworks to do in this tube. Go to the page number 14 now. Yeah, in the page number 14, right? So page number 14 and 15 mark these MCQs. First one, second one, and then question number 6, first, second, 6. Then seventh one, question number 9. In 2023 A-level MCQ, you can try statements 1, 2, and 3. 1, 2, and 3. In 2023 A-level MCQ, statement 1, 2, 3. In 2024 A-level MCQ, statement 2 and 5. Statement 2 and 5. Okay. And then 2024 A-level SCQ 1, A4. Last statement. No. Page 50. We are still in the page 50. And page 15, try the possible questions for you. Shall I tell again? One more time. Because page 15, question number 7, you can try. Question number 9, you can try. In question number 2023 A-level MCQ 7, you can try statement 1, 2, 3. 2024 A-level MCQ 8, you can try statement 2 and 5. And then the last step. And then go to the next page. Page number 16, you have to try as a homework. It contains some good statements about shielding effect, ionization energy, and the factors affecting period properties. Remember the second page table we prepared last week. Everything increases except attraction downward the group. Attraction downward the group, this decreases. Everything else increases. So to remind those facts, try to page 16, the full page words. And page 17, 18, questions now, page number 17. You have 50 statements, you can up to 36. And to 36. Much of formulas I know, but and you can try that structure is yours. Page number 9. Ionization energy, few MCQs are left. I'll discuss them in the next day. Please remind me on it. Online students, please remind me. Ionization energy, MCQs, remaining MCQs. Okay, so what did we discuss today? Radius and electronegativity. Electronegativity is a small topic. What we discussed mainly is radius. So there are two types of radii, atomic radii and ionic radii. For both, we can apply Z. Okay? They will only ask questions that we can apply Z. They are asking Z. Right? And we know why we can't measure the atomic radius exactly. And the solutions were using covalent radius, metallic radius, and van der Waals radius. You need to know what this stands for and simple idea about bonding is enough. Anyway, we're going to discuss those metallic bonding and everything again later. And then we discussed how downward the group radius increases, the first period it decreases. And we did some questions. And then after that, we came to ionic radius. Cations are always smaller than parent atoms, anions are always larger than parent atoms. Not only that, we had mirror set for that too. And not for all, for anions, we can easily apply that. For cations, only sodium, so lithium, beryllium, sodium, magnesium, we could apply. Others, it didn't apply, we couldn't apply. And then there were some special points, isoelectronic series. Remember that, and that was their frequent in MCQs. And then special points. What are the special points? Anions are larger than their neutral atoms. That means N3 minus, O2 minus, F minus are larger than nitrogen. Cations are smaller than their parent atoms. Opposite statement. Sodium plus aluminium 3 plus magnesium 2 plus, they all are smaller than aluminium. Aluminium is the smallest atom now. Sodium, magnesium, aluminium. Their cations are smaller than aluminium. Okay. But like that, there were some other points too. Okay. Yeah. The fourth period cations were larger than second period anions. Right. What else? There's one third period, fifth period cations. And fifth period cations are larger than third period anions. There's one. Right? Sodium neon point. Sodium is larger than neon. That also value. So like that, there are points. Actually, sodium neon thing now, basically because of the measuring method. So, and we can't explain it using the theories. And yeah, I mean, those are the things we discussed. So try the MCQs again, go through that theory part again. And try those questions I told you. So last week we did a very important thing, factors effective review properties. You need to get the recording, so send me a message. Today's tute, you have the number. Send me a message. I'm looking today. I need the last week report. Okay. Right, Laman. So let's meet again next day. This week we are doing the paper class. Okay. 2 weeks, 3 weeks. Yeah, I remember. Hydrogen emission spectrum. I think we did only one structured essay. The last structured essay is there to discuss them. We'll discuss that this week. Right, so goodbye. Go safe. Right? Goodbye. Goodbye. Okay, online students. See you again next day.